Take a metal bar. Heat one end with a flame, then take the flame away and watch. You already know roughly what happens. The heat spreads out, the sharp difference between hot and cold softens, and after long enough the whole bar settles at one lukewarm temperature. Now make it harder. Suppose the starting temperature is not a smooth hump, but a jagged mess, hot in places, cold in others, with sudden jumps between them. Predict the temperature everywhere, at every future moment. In 1807, a French administrator handed that answer to the Paris Institute, and Lagrange refused to accept it. The paper was called On the Propagation of Heat in Solid Bodies. Its author was Joseph Fourier, who was at that time the prefect of Isère, running a French department from an office in Grenoble. He had been a teacher, then a revolutionary, then very nearly a victim of the revolution, then one of the scholars Napoleon took to Egypt. He came back, was handed an administrative job, drained the swamps of Bourgogne, oversaw a road to Turin, and in whatever hours were left he worked on heat. What he produced was a way to solve the problem completely. What made it unacceptable was the thing he had to assume to get there, and the argument about that assumption ran for 15 years, before his book finally appeared in 1822. So let me show you the problem the way he met it, because the difficulty is not obvious until you try. Here is the bar again, and here is its temperature drawn as a curve. High where it is hot, low where it is cold. As time passes, that curve changes shape, and the rule for how it changes is simple to state. At every point, the temperature climbs or falls at a rate set by how curved the graph is at that point. Where the curve dips down into a valley, that spot is colder than its neighbors on both sides, so heat flows in and the temperature rises. Where the curve arches up into a peak, that spot is hotter than its neighbors, so heat drains away and the temperature falls. Curvature drives the change. That is the heat equation, in words, and it is genuinely a complete description. Give me the shape now, and the rule tells me the shape a moment later. But a rule for a moment later is not a solution. If you want the temperature after an hour, you would have to apply that rule again and again, and each time you apply it, the shape changes. So the rule you apply next is working on something new. Every point depends on its neighbors, and its neighbors depend on theirs, and the whole bar is tangled together. Step forward far enough, and the arithmetic is hopeless. Fourier wanted a formula. Not a simulation, a formula. One you could write down and evaluate at any time you liked without grinding through the hour that came before it. And there is one starting shape where you can have exactly that. Suppose the bar does not start as a jagged mess. Suppose it starts as a single clean wave, one smooth arch of a sine curve, hot in the middle, cooling to the ends. Apply the curvature rule to that shape, and something very convenient happens. Near the peak, the curve arches down hard, so the peak drops fast. Halfway down the slope, the curve is gentler, so that point drops more slowly. At the ends, the curve is flat and nothing moves at all. Work out how much each point falls, and the amounts are in exact proportion to how high each point started. The half-height point falls at half the rate of the peak. Every point drops by the same fraction of itself, which means the shape survives intact, still a sine curve of the same width in the same place, only shorter. Wait, and it shrinks again by the same fraction, sinking towards zero and keeping its form all the way down. That is a solvable problem, and it is the formula he wanted. One sine curve in, and the answer for all time is that same curve multiplied by a number that shrinks as time passes, and the wavelength decides the speed. A long, lazy wave is barely curved anywhere, so it fades slowly. A tight, rippled wave is sharply curved everywhere, so it collapses fast. Squeeze the wave to half its width, and it does not fade twice as fast. It fades 4 times as fast, because the curvature goes up with the square. That factor of 4 is going to matter later, so hold on to it. The trouble is that nobody's bar starts as a sine wave. Here is where he made the move that got him rejected. The heat equation has a property worth stating plainly. because everything downstream depends on it. If you have two starting shapes, and you know how each one evolves, then the shape you get, by adding them together, evolves into the sum of the two answers. Each one cools as though the other were not there, and the temperature you measure is just the total. So sums of solvable things are solvable. Two sine waves, or 10 or 100, each one fading at its own rate. Then Fourier asked the question the whole video rests on. What if every starting shape is a sum of sine waves? Not approximately, and not for the nice ones only. Every shape. The jagged mess, the sudden jump, the flat line with one spike in it. If any temperature profile you can draw is secretly a pile of sine waves added up, then the heat problem is finished, because he could already solve every one of those pieces. Now, look at what that claim actually asks you to believe. A sine wave is about as smooth as a curve can be. It has no corners anywhere. Add two smooth curves and you get a smooth curve. Add 1,000 and it is still smooth. Fourier was claiming that if you add the right infinite collection of these perfectly round, cornerless waves, you can produce a shape with a corner in it, a vertical cliff, jumping from cold to hot, with nothing in between. Lagrange did not believe it, and he was not being obtuse. He had worked on the vibrating string decades earlier, and he had gone a long way into this exact question and stopped short of Fourier's claim. Daniel Bernoulli had proposed something similar for the string back in the 1750s, and Euler and D'Alembert had argued against it then. Nobody claimed the sums were useless. The objection went deeper than that, because a sum of smooth pieces ought to come out smooth, and a sum of pieces defined by one formula everywhere ought not to be able to imitate a function that behaves one way on the left and a different way on the right. The Institute set the propagation of heat as its prize subject. Fourier entered a revised version, and he won. The committee, which included Lagrange and Laplace, gave him the prize and then declined to publish the paper, noting that the way he got there left something to be desired in rigor. Their complaint about the rigor was fair, and his claim was also true, which sounds like a contradiction until you realize it took another generation to build the language in which both could hold at once. So let us take the claim seriously and ask the practical question. Suppose it is true, and every shape really is a sum of sine waves. That is no use to anyone unless you can find out which ones, and how much of each. This is the part of the story I find genuinely clever, and it is where the video stops being history. Write the unknown mixture out. Your temperature shape equals some amount of the first wave, plus some amount of the second, plus some amount of the third, and onward forever. You know the wave shapes already, and the amounts are what you are missing. So you have one equation and infinitely many unknown numbers in it, which normally means you are stuck, except that these particular building blocks have a property that lets you reach in and pull out any one of them on its own, and ignore all the rest. Here is the property. Take two different sine waves from the list, multiply them together point by point, and add up the result across the whole bar, the area under their product, rather than the area under each of them separately. Do that, and you always get 0. That is worth seeing rather than believing, so take the simplest case, the first wave and the second. The second wave completes 2 full cycles, while the first completes 1. Line them up and look at the left half of the bar. There, the first wave is positive throughout, and the second wave runs through a complete cycle of its own, up then down, spending exactly as much time positive as negative, and reaching the same height either way. So the product is positive for a stretch and then negative by a matching amount, and the two cancel exactly. Now the right half. The first wave is negative throughout. The second again runs a complete cycle. And the same cancellation happens with the signs flipped. That is the decisive step. So here is what it buys you. Take your unknown mixture, multiply the whole thing by one particular wave, say the 7th, and add up across the bar. Every term on the right dies except 1, because the 7th wave against any wave that is not itself gives 0. The only survivor is the 7th wave multiplied by itself, and that one gives half the bar length times whatever unknown amount of the 7th wave was in the mixture. That leaves a single equation with a single unknown. Divide, and you have the amount, and you can do it for any wave you like, one at a time, forever. The infinite tangle came apart because each piece was built to be invisible to all the others. That is the decisive step, so here is what it buys you. Take your unknown mixture, multiply the whole thing by one particular wave, say the 7th, and add up across the bar. Every term on the right dies except one, because the 7th wave against any wave that is not itself gives 0. The only survivor is the 7th wave multiplied by itself, and that one gives half the bar length times whatever unknown amount of the 7th wave was in the mixture. That leaves a single equation with a single unknown. Divide, and you have the amount, and you can do it for any wave you like, one at a time, forever. The infinite tangle came apart because each piece was built to be invisible to all the others. Let me put a real shape through it, because a method you have not used on anything concrete is not yet a method you own. Take a bar that starts hot on one half and cold on the other, with a jump in the middle. That is the hardest case Lagrange objected to, so it is the fair one to try. Run the procedure. Multiply the shape by the first wave and add up across the bar. Because the shape is just a constant height on the left and the same height negative on the right, that sum is easy to picture. On the left, the first wave is positive and the shape is positive, so the product is positive everywhere. On the right, both flip sign together, and a negative times a negative is positive again. Nothing cancels anywhere. Every scrap of area adds, which is why this wave scores as high as it possibly could. Now try the second wave. On the left half, where the shape holds one steady value, that wave runs a complete cycle and averages to nothing, so the left half contributes 0. The right half does the same. The second wave scores nothing at all. The third wave is the interesting one. Across the left half, it completes 1.5 cycles. So one full cycle cancels itself and a half cycle is left over. That leftover is what survives. And it is a third of the size of the first wave's leftover, because it is 1/2 cycle out of 3 rather than 1 out of 1. Carry that through and the pattern is forced. Every even-numbered wave averages to nothing against a shape that is flat on each half. Every odd-numbered wave keeps exactly 1/2 cycle out of however many it runs, so the amounts fall off as 1, a third, a fifth, a seventh, dropping in step with the wave number. So the recipe for a square jump is the first wave, plus a third of the third wave, plus a fifth of the fifth, forever, all of it scaled by 4/pi. That leading factor is what makes the shelves sit at the right height rather than merely the right shape, and it drops out of the same integral once. Watch it assemble. One wave alone is a poor imitation, a single round hump where a flat plateau should be. Add the third wave and the hump flattens on top and the sides steepen. Add the fifth and the flat gets flatter, the sides steeper. Keep going, and the smooth arch turns into something with 2 level shelves and a near vertical wall between them. The corner is being built out of curves. Every piece you add is perfectly smooth, and the pile of them is heading somewhere that is not. Now, Lagrange was not simply wrong, and this is where the honest version of the story matters. Look closely at the jump as the waves accumulate. Right at the edge, the sum overshoots. It climbs past the true value, ripples, and comes back. Add more waves and the ripple gets narrower, squeezed toward the jump, but it does not get shorter. That overshoot stays at about 9% of the jump, no matter how many terms you take. Henry Wilbraham found this in 1848, and almost nobody noticed. 50 years later, Josiah Willard Gibbs described it while studying square waves, and got it wrong in his first note and corrected it in the second. In 1906, Maxime Boucher analyzed it properly and attached Gibbs's name to it, which is the name it still carries, though Wilbraham had it first. So the series does reach the square wave at every point away from the jump. At the jump, it splits the difference, and just beside the jump, there is a permanent bump that never flattens out. Fourier's claim survives, but only once you are careful about what converging is supposed to mean, and pinning that down was a large part of 19th century mathematics. Dirichlet gave the first real proof of convergence in 1829, 22 years after the memoir and 1 year before Fourier died, and he had to state conditions on the function to do it. Now let us finish the heat problem, since that is what all this was for. You have a bar with any starting temperature you like. Break that shape into its sine waves using the procedure. Each wave fades on its own, at a rate set by how tightly it ripples. Let each one shrink by its own amount, add them all back up, and that sum is the temperature everywhere, at any time you name. A formula, exactly as he wanted. And look what it explains for free. The tight ripples are the fine detail in the starting shape, the jagged bits, the sharp corner, and those are the modes that die fastest. The long, slow waves are the broad overall imbalance. Hot end against cold end, and those hang on longest, so heat smooths things out, and not as a vague tendency. It is an arithmetic consequence. Roughness is made of exactly the components with the shortest lifetimes, so it is the first thing to go. Wait long enough, and every mode has faded except the flat one, and the flat one is the average temperature. The bar goes lukewarm because that is the only shape that has nothing to decay. The physical problem is solved, and underneath it there is something larger, which is the reason this technique escaped from heat and turned up in almost everything. Go back to the trick. Multiply two things together, add up the result, and see whether you get 0. If you have met vectors, that should feel familiar because that is a dot product. Take two arrows, multiply their matching components, add the products, and a result of 0 means the arrows are at right angles. Fourier's operation is the same operation. The only difference is what counts as a component. An arrow in 3 dimensions has 3 numbers in it, so you multiply 3 pairs and add 3 products. A temperature profile has a value at every point along the bar, which is infinitely many numbers. So you multiply at every point and add them all up, and adding up a value at every point of a continuous range is what an integral is. So the integral was a dot product all along, on lists that are too long to write down. Then everything else in the story translates, and it translates exactly. 2 sine waves whose product integrates to 0 are perpendicular. The list of sine waves is a set of mutually perpendicular directions, which is to say a coordinate system. Finding how much of the 7th wave is in your shape is measuring the shadow your shape casts along the 7th axis. Writing a function as a sum of sines is giving its coordinates. And this is the sentence the whole video has been walking toward. Functions behave like vectors. A temperature profile is not a curve you draw, it is a point in a space. And Fourier found a good set of axes for that space. Once you say it out loud, the strangeness moves. The surprising thing is no longer that a corner can be built from smooth waves, because in this language, that claim is much more modest. It says a particular point in the space can be reached using a particular set of axes. That is a statement about whether your coordinate system covers everything, which is a reasonable thing to ask, and, with care, to prove. But it leaves one question open, and it is the one I think is the real prize here. Why those axes? Space does not come with directions painted on it. You can describe a vector using any set of perpendicular directions you like. So of all the coordinate systems available for functions, why did sine waves turn out to be the useful ones for heat? The answer is that heat chose them, not Fourier. Remember what the heat rule does. It takes a shape and hands back the curvature of that shape. It is a machine that eats a function and returns another function. Feed most shapes into it, and what comes out is unrecognizable. Some new curve with no obvious relation to what you put in. But feed it a sine wave, and it hands you back the same sine wave, scaled down by a number. That is the whole reason the method works, and it has a name. In ordinary vectors, a matrix usually takes an arrow and swings it to a new direction. For a few special arrows, it does not swing them at all. It only stretches or shrinks them, and those are the eigenvectors of the matrix. The number they get multiplied by is the eigenvalue. Sine waves are the eigenvectors of the curvature machine. The tight ones have large eigenvalues, which is why they decay fast. And the 4 times factor from earlier is that eigenvalue being proportional to the square of how tightly the wave ripples. So the reason Fourier's method dissolves the heat equation is not that sine waves are pretty or familiar. It is that they are the directions in which the heat operator does nothing but scale. Choose coordinates built from those directions, and a problem that tangled every point together turns into infinitely many separate one-line problems, each one a single number shrinking. Choose any other coordinates, and the tangle stays. That is a general principle, and it is why this keeps reappearing. Find the operator that governs your system, find the shapes that it merely scales, use those as your axes, and the hard problem falls apart into easy ones. Different operator, different natural waves. The technique is the same, which brings us to the last step, and it is the one the mathematicians took rather than the physicist. The collection of all functions is a space, and one question about that space is harder than any we have asked. Write down an infinite sum of perpendicular pieces. Is there guaranteed to be a function sitting there for it to converge to? Or can the sum point at a gap where nothing exists? For ordinary vectors, that worry does not arise. In infinitely many dimensions, it very much does. And the answer depends on which functions you agree to admit into the space. Riesz and Fisher settled it independently in 1907. If you allow the right class of functions, the ones whose squares have a finite total area, then the space has no gaps. Every sum of perpendicular pieces that ought to converge does converge to something that is genuinely in the space. The geometry is trustworthy. That space is the one David Hilbert had been circling in his work on integral equations, and the name came later. In a series of papers finishing in 1929, John von Neumann laid out the abstract structure, and it is his phrase that stuck. Hilbert space is a space where you can measure lengths and angles, with infinitely many dimensions, and no holes in it. And then quantum mechanics arrived and turned out to be written in exactly that language. A quantum state is a vector in a Hilbert space. Measurable quantities are operators on it. The possible outcomes of a measurement are that operator's eigenvalues, and the states that give a definite answer are its eigenvectors. Every one of those words has appeared in this video already, and all of them came out of a question about a hot metal bar. Von Neumann had the mathematical structure in place before it was needed. It was ready because Fourier had asked how a bar cools, so the complete story runs like this. A prefect in Grenoble wanted a formula for heat and found that one shape, the sine wave, keeps its form while it fades. He claimed every shape was a pile of those, which was rejected, and was true. Pulling out the pieces one at a time works because different waves multiply and cancel to nothing, and that cancellation is perpendicularity in disguise. Perpendicularity means the functions were vectors the whole time. Sines were their axes, and those axes were chosen by the heat operator rather than by Fourier, because they are the shapes it merely scales. Make that geometry rigorous, and you have Hilbert space, and it was waiting when physics needed somewhere for a quantum state to live. Look at the bar one more time. A temperature along it, cooling. In Fourier's hands, that is a point in an infinite dimensional space, drifting toward the origin along infinitely many axes at once. The far ones racing in, the near ones dawdling, until only the average is left. It is the same bar. It always was. There is one thing I have quietly avoided the whole way through. Everything here lived on a finite bar, which is why the answer came out as a sum of separate waves with whole numbers of cycles. Let the bar become infinitely long, and those separate waves crowd together until they are no longer separate at all. The sum turns into an integral, and what you get is the Fourier transform, the version that runs your phone calls and your compression formats and your medical scanners. That is the next film, and if you want it when it lands, subscribe. Fourier never saw any of it. He got the prize, waited 15 years for the book, and spent his later years arguing that the atmosphere holds in the planet's heat, which was right too. He died in 1830, 1 year after the first proof that his series worked.